Welcome to this lecture series in real analysis. We are starting a new module, and in this lecture, we'll look at the notion of open sets, which is very important in real analysis. All we need to know is what are intervals. So if we have two real numbers, let's say a and b, and if a less than b, then we can define this interval, which is all real numbers which are strictly between a and b. So this is an open interval. This is also an open interval, minus infinity comma b, which is all real numbers strictly less than b. And similarly, we have this guy. So these are all the open intervals. And there are other kinds of intervals, which are closed intervals or semi-closed and this that, but essentially we will need the notion of open intervals. Okay. Here are some problems for practice. And now let us get started. So let us define an open set. We have the notion of an open interval, but based on that notion, we will define what is an open set. So a subset U of R is said to be open if for all points in U, there is an epsilon greater than 0, such that this open interval is contained in U. Right? So the idea is that if for every point in U, there is some room around the point, meaning you can think of this as a breathing room around the point, which is contained in U. So you can accommodate sort of a breathing room for every resident in it. I can draw a picture right now, but this will be clearer when we look at more examples. So an open set will look something like that. Something like that. So if you take a point here, then there is a breathing room around it, or any point here, there is a breathing room around it. So the union of these two shaded things constitutes an open set. All right, we will look at examples and this will be more clear. We should note that by convention, the empty set is open. Right? So we should remember this convention. And every open interval is also open, naturally. So if you pick an open interval, let's say, let me not write down a formal proof of it, but let me just explain via picture. So we have this real line, and this is an open interval. Let's say this is A and that is B. Then if you pick any point here, you can find a room around it, which is contained in the open interval. So if you want to be very formal, then you can say that, okay, if you pick a point X in the open interval A comma B, then you can choose epsilon as the minimum of X minus A and B minus X, and then X minus epsilon comma X plus epsilon. This open interval would be contained in A comma B. I hope I'm not making a calculation mistake, but anyway. So, and every open interval is open. I illustrated this for a finite interval, meaning where both the endpoints are real numbers, but the same argument will go through for semi-infinite in open intervals. All right, a more general example is what I already illustrated here. I mean, this example is really that example. So by this example, what do I mean? I mean, let's call them something. Let's call this A1, this is B1, this is A2, that is B2. So this point is A1, that is B1, this is A2, that is B2. And you define capital U as the union of these two open intervals. Then U is open. You may want to write down a formal proof of it, but it's very, very easy. And now let us look at an example of a non-open set. So simplest example would be just a singleton. So you define U as, let's say, 3. This is a subset of reals. This is not an open set because, well, when you choose a point in it, the only thing you can choose is 3. And if you make a room around it, meaning choose a positive epsilon and consider the open interval centered at 3 with radius epsilon, of course, that thing will not be contained in U. So that is one example, but a more somewhat interesting example would be any closed interval, let's say 2, 3. So this is not an open set. Why is that? Let me not call it U then. Let me call it F. So why is F not open? So here is what F looks like. Everything between 2 and 3 and including 2 and 3 is F. And why isn't it open? The reason is very simple. You pick this point in F and make a room around it. That room cannot be contained in F. So for points inside, for points strictly inside, of course you can make a room which is contained in F, but these boundary points cause problem. So this is not an open set. Okay, enough of this. And now there are some properties of open sets. So here is the first property, that the intersection of any two open sets is open. Right? So let us prove it properly. So let U and V be open subsets of R. And if their intersection is empty, then we are done, because the empty set is open by convention. So we may assume that the intersection is not empty. Alright, so the intersection is not empty, and now pick any point in the intersection. We want to show the intersection is open, so pick any point in the intersection. We want to show that there is some room around the point which is contained in the intersection. So since U is open, there exists some epsilon greater than 0 such that x minus epsilon, x plus epsilon, this interval is contained in U. And since V is open, there exists some delta greater than 0 such that x minus delta, x plus delta is contained in V. Okay. And now if you take theta as the smaller of epsilon and delta, then we have this is contained in the intersection. Why is that? Because, sorry about this, what is going on? Yeah, I hate notability. So why is that? Because this is contained here and this is also contained there. And this in turn is contained here and this in turn is contained there. So this is contained in both of them and hence in the intersection. Now this finishes the proof, because we just wanted to exhibit a positive theta. So note that theta is actually positive because both epsilon and delta are positive, and the minimum of two positive numbers will only be positive. So that's it. So we have exhibited a room around the point x which is contained in the intersection. That finishes the proof. But what is going on? What is going on is very, very simple. What we have is, we have this some set U. Let me try to shade it. I'm not going to be very, very good at that, but anyway. So let's say this is U. Well, I've really drawn an open interval. Let me be a little bit more generic. So let's say that is U. So the shaded thing in gray is U, and let me use some other color. Maybe let's use yellow, which is horrible. But let's say this is V. Let's say the yellow thing is V. And now if you pick a point, I mean, this looks yellow in the dark background, in the light background, I don't know if it will look yellow or not. So if you pick a point, let's say in the intersection, then you can find a room around the point which is contained in the in U, and find another room around it which is contained in V, and all we are doing is we are picking the smaller of the two rooms. The smaller of the two rooms will be contained in both of them, and that's it. That is the argument. So nothing very complicated going on. The best way to understand such things is to prove them by yourself. Okay. The next property is that is just a consequence of the previous one. The intersection of any finite collection of open sets is open. Because we have proven it for two open sets, it just follows by induction that it also holds for any finite collection. Just keep applying the same proposition repeatedly. So that's fine. And the intersection of an infinite collection of open sets may not be open. So let's see why. You can't just, you can't be careless about this. So why is that? Just define un as this interval. Pictorially, we have 0 here. This is 1 minus 1 by n, that is 1 by n. And as n increases, your uns shrink. So in particular, what we have is u1 contains u2, contains u3, and so on. We have a nested shrinking sequence of open sets. But what is their intersection? If you intersect all of them, you'll get the singleton 0. Why? Because clearly 0 is in each of the uns, so this intersection contains that thing, the singleton 0, but no positive or negative real can be here. First, why is it that no positive thing is here? The reason is the infimum of this set is 0. So beyond a certain large enough n, if you pick some positive number, call it epsilon. When n is large enough, 1 upon n is smaller than epsilon. So if epsilon is here, for large enough n, 1 upon n is smaller than epsilon, and hence epsilon cannot lie in un, and hence cannot lie in the intersection. So that's the reason why this is the singleton. It should also be intuitively clear because you're shrinking and shrinking and shrinking, and after a certain point you will converge or collapse to 0. Fine, so this intersection is the singleton 0, and the singleton 0 is not an open set. No singleton is open. So this is not an open set, and that's it. So the intersection of an infinite collection of open sets may not be open, even though in the intersection of any finite collection of open sets is always open. Alright, so these are some properties of open sets with regard to intersection. This is one property which is with regard to union. So the union of any collection of open sets is open. Finite, infinite, uncountable, whatever. If you have a family of open sets, their union will be open. Let's prove it. Let's write down a proof. So let us say we have the script U be a collection of open sets. So what are we saying? There is some indexing set J. Usually our indexing sets have been natural numbers, but now what we are saying is that just pick a set which indexes open sets. So for each element in this indexer, we have an open set. So we have a family of open sets. The cardinality of this family could be huge, could be uncountable, that's okay. What we want to do is, if we define U as the union of all the things in script U, want to show that this is open. And it's just to follow your nose argument. Pick some point in U arbitrarily. Then by definition of union, there is some alpha in the indexer such that x is in U alpha. What's going on? We pick something here, then it has to be in one of the things. I mean, this is a union of a bunch of things, so if if you pick an element here, it has to be in one of the things whose union is U. Fine, so pick some alpha such that X is in U alpha. There could be multiple such alphas, but we just pick one. And now you use the fact that U alpha is open. There is some epsilon greater than 0, such that this open interval is contained in U alpha, which implies this open interval is also contained in U, because U alpha is contained in U. And that's it. That proves that U is open, and hence the union of any collection of open sets is open. So these 2-3 properties of open sets should be remembered. The first is the empty set is open. The second is that the intersection of any finite collection of open sets is open. And finally, the union of any collection of open sets is open. And let me also maybe write down here itself that the set of all the real numbers is open. This I should have taken as an example earlier. The set of all the real numbers is open. This is obviously open. So nothing to do there. Fine, let's proceed. So now there is this notion of interior of a set, motivated from the notion of open sets. So first we have the notion of open intervals. We generalized that notion to the notion of an open set. You can think of open sets as a sort of a generalization of open intervals. And now we will sort of even further generalize that notion in some sense. So what we are doing, we have any subset of the reals, let's say non-empty. I don't know what can we say about the empty set, but let's say this is non-empty. For empty set, it is just a matter of convention. Whatever be the convention, I'll have to see. We can make our own convention. So fix a non-empty subset of the reals. The interior of S is defined in the following way. So the interior of S is defined as, notation is S and then you make a small 0 in the superscript, 0-like symbol in the superscript. This is all those points in S for which there is some room around it, which is contained in S. So those points in S such that there is an open set U with the property that, or such that, X is in U and U is contained in S. Okay. Looks like a convoluted definition. All we are saying is the interior of S is all those points which have a breathing room around them contained in S. Writing an open set or open interval here will not make any difference to the definition. So please be mindful of that. I could have just said that there is an open interval U such that X is in U is contained in S. Or I have written an open set. It doesn't make any difference. Even though the definition of an open set is not the same as that of an open interval, it doesn't make any difference to this definition. All right. So that's the notion of the interior, and this definition will be more and more clear as we look at examples. So the first example is this. You have the singleton. What is its interior? Nothing. Nothing is its interior. So here the interior is empty, because the only point in S is the number 1, and if you make a room around 1, it cannot be contained in S. So this is empty. More generally, if you have a finite subset, same thing. This is also empty. Maybe you should supply a proof of it. If it is not immediately clear why this holds for finite sets, just start with doubletons. For singletons, we have seen, start with doubletons, meaning 2-element sets, and then try to extend that reasoning to finite sets. All right. What about this guy? So pictorially, this is A, that is B. Clearly, if you take a point inside, strictly between A and B, then you can make a room around it and have that room contained in S. But if you take these endpoints, no room around these endpoints is contained in S. So without writing any details, the interior of the interior of this thing is the open interval a comma b. All right. And now what about the set of rationals? If S is the set of rationals, what is its interior? Well, if there were an open set which was contained in the rationals, then that open set would be devoid of all the irrationals. But the irrationals are dense. We have seen that the rationals are dense, but by the same kind of reasoning, the irrationals are also dense. I'm sure this was given as an exercise at some point. Or maybe I proved it, I don't remember. But the irrationals are dense in the reals, and hence no open set can be contained only in the rationals, except for the empty set. Empty set is open and it is contained in the rationals, but except for that, any non-empty open set cannot be contained in the rationals. And therefore, the interior of the rationals is empty. So please make sure you understand that reasoning. Right? So some nice examples. And let's maybe finish the lecture with this. So here is a reformulation of openness. A subset U of R is open if and only if U is same as U interior. Right? So let's prove this. So if U is open, then U is U interior. This is fine. This is very, very simple. Well, if U is open, then every point of U has a room around it contained in U, and hence every point of U is in the interior of U. So this containment is clear, but U interior is always contained in U. U interior, no matter what U is a subset of U, and hence U is equal to U interior in this case. So that's the reasoning. And now if U is equal to U interior, then for each point of U, there is a room around that point which is contained in U. That's the definition of interior. And that's, by definition, gives you that U is open. So nothing much to write here. You can write more details if you like, but this is more or less a straightforward proof. All right, so a subset U is open if and only if it is equal to its own interior. And more generally, you pick any subset of the reals, then the interior of it is the union of all the open sets that are contained in it. Okay, so this is a generalization of the previous proposition. And before we write down a proof, what this is saying is that, in some sense, the interior of S is the largest open set that is contained in S. You're taking the union of all the open sets which are contained in S, and that we are claiming is equal to the interior of S. Therefore, interior of S is the largest open set that is contained in S. So that is the idea of the interior. The interior was defined to capture that idea, how open a set is. All right, whatever. Let's prove it. Okay. So let this be the collection of all open sets which are contained in S. So this is script U. Script U is the collection of all open sets which are contained in S. Okay. Now note that if U is in script U, then U is contained in the interior of S. So this is a piece of, this is very, very easy, but one should be very clear why this is true. Let me explain via a picture. So we have some set S, which I don't want to draw anything about it, but we have some set S. And now suppose U is an open set which is contained in S. We are claiming that U is also contained in the interior of S. Now if U is an open set contained in S, and you pick a point in U, then clearly U itself is an open set which contains that point and is contained in S. So any point in U is in the interior of S. It is immediately from the definition of the interior. Okay, so this, please be very sure you follow this. And therefore, one thing is clear, that this implies the union of all the things in U, the union of all the things in script U is contained in the interior of S. Alright? Fine, but here I could have just noted that, note that S interior is a member of script U. S interior is an open set contained in U. Right? Maybe I should have proved it at some point. So the interior of any set is open. I didn't prove it. So if you take the interior of anything, it is going to be an open set. Yeah, that should be proven. So let me prove that. So the last thing that is needed to be proved is that, note that S interior is an open set, and it is contained in S by definition, but it is an open set. So why is that? To prove this, let X be in the interior of S. Then there is some open set V such that X is in V and V is contained in S. Okay. But then every point of V is in the interior. So if you have an open set contained in S, every point of that open set is in the interior of S. Fine? So actually V is not just contained in S, V is contained in S interior. So there is a room around the point X which is contained in the interior of S, and therefore S interior is open. Seems like a convoluted piece of reasoning, but it is not. It's very, very simple. So S interior is open, and it is therefore contained in the union of all the things in script U, because S interior is therefore a member of script U. So this containment here, follows from the blue claim, because S interior, or the interior of S, is a member of script U, and hence it is naturally contained in this union. So this sandwich tells us that S interior is this union, and that's it. So the interior of S is the largest open set that is contained in S. Yeah, so I should have proven this separately, that S interior is always open. Somehow I forgot that. But surely you can supply your own proofs when it comes to things like this. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.